Welcome to the last origin seminar of this semester. And today we have the Griselda. And Shuo, do you want to give an introduction?
Yeah, sure. Yeah, sorry, I can't be there in person today. But let me introduce Griselda. So Griselda Arroyo-Chavez just graduated from UNAM last October, working with Enrique Vasquez-Semedeni. And her work is on numerical simulations of a molecular cloud and star formation with a focus on understanding the angular momentum across different scales. She joined STORD last November to continue work on the similar subject. So today she's going to tell us about her work on the angular momentum and star formation. So Gris, go ahead.
Thank you so much for having me today. I would have loved to be there with you in person. But yeah, after a conference last week, I just arrived in Tucson yesterday with a flu-like symptom. So just to be sure that I'm not contagious or something, I decided to present online. But if you have any questions or comments, my office is 332. So you're very welcome. So today, as you said, I'm going to talk about the angular momentum in molecular cloud to core scales, specifically about the evolution and angular momentum redistribution during the gravitational collapse and fragmentation process. And I study this subject using numerical simulation. So first, okay. I'm going to give you a brief introduction on the angular momentum and molecular cloud scales. Then our problem, or the questions that we want to solve and our goals. Then we're going to have the first part, which is more related to the evolution of this angular momentum during this process. And the second part will be more related to the nature of this angular momentum transport mechanism. Of course, we're going to have conclusions for both parts, and finally what I'm doing now. So we are talking about molecular clouds, so these dense cold regions with gas and dust where stars form. And during this star formation process, there are too many things happening, but of course I'm going to focus on the angular momentum. So if the angular momentum is conserved during this contraction, so imagine that the molecular cloud is contracting to form just one single star, like connecting, just collecting all of the material to form just one single star, then the resultant star should rotate so fast that it will fly apart. So in order to have star, we need to remove some angular momentum during this process. And this apparent non-conservation of angular momentum is what we know as the angular momentum problem at this scale specifically. So if we take a compilation of different objects with different sizes, so clouds, clumps, and we plot them in this JR relation, so we have on the y-axis the specific angular momentum, this little j, versus radius or size in the x-axis. If the angular momentum is conserved, we would expect to see a constant line. But what we see is actually something more like this. So this is, again, the JR relation, but this is a compilation of different observational samples where you can see that the larger structure in the top right have more angular momentum per unit mass compared to the smaller objects. So we know that in general, this little j goes as the radius to the 1.5, 1.8. But this problem is kind of an old problem, so it has been there since the 70s, 80s. So over the years, some solutions have been proposed to solve this angular momentum problem at these scales. We could have magnetic braking, so involving magnetic field. So I think these people are more related to this magnetic braking process. We also have gravitational torques, turbulent viscosity, and pressure gradient torques. But it's not strange to have all of these possible solutions, because if we write the analogous equation of R cross P, but taking P as the momentum equation for fluids, then cross product with a position vector and integrate it over a volume, Then the terms on the right-hand side are actually the active torques, and we see here the magnetic, gravitational, pressure gradient, viscous torque, and the one that we call as hydrodynamical torques, which includes turbulent viscosity. So here something to distinguish, we have the viscosity or the viscous term, which is like the microscopic viscosity, and the one that is related to turbulent viscosity, which is not like microscopic viscosity. It can work in the same, something similar, but it's like different. So the thing is that we have all these possible solutions, but in general, what we have is an interplay between these three ingredients. So we have turbulence, gravity, and magnetic field. So the questions we want to solve here are first, if do stars form from material with unusual low angular momentum, what physical processes, by what physical process, and at what point, at what stage we are losing this angular momentum. This angular momentum is being transported out of the cloud, out of the clump. And we want to understand the origin of this JR relation, so specifically this slope, this 1.5 slope in the JR relation. Our goals is to try to offer an answer, an explanation for the angular momentum problem using numerical simulations, but also try to quantify the relative importance between these three ingredients: gravity, turbulence, and magnetic field. So let's move to the part 1. So we have the angular momentum evolution. As I say, we use numerical simulations. In general, my simulations are about the formation and collapse of giant molecular clouds in the warm neutral medium. I use specifically SPH simulations, so particle simulation. These are simulations of 256 parsecs per side. This in particular, the first that I studied, was performed with the Code Gadget 2. And here we have decay and turbulence, self-gravity, cooling and heating functions, but no magnetic field and no stellar feedback. The point here is try to define a numerical sample of clumps using a criterion by density threshold. So we choose like different density threshold to define a sample of clumps at what we see in the observations. But we also are interested in the evolution. So we track those clones, the clones we define, from the past and to the future. We perform different ways, different methods of tracking clumps. Here, the first way to track clumps is a Lagrangian structure. So again, we have these SPH particles, so we have particles. And in the case of tracking from the past, which is this first row, the definition time is on the right. So here we have these red particles. This is the definition time, so we applied our density threshold algorithm there. These member particles are in red, and as we go back in time, we can't always track the same set of particles using their ID. So in the past, these member particles are more dispersed, but also some other that we call intruder particles in blue appear in between the original particles. We also track these clumps to the future. So in the case is the row at the bottom. The definition time is on the left. And as time passes, we can see that these clumps can develop a center of collapse, but we also have other intruder particles, so these blue particles. We also track clumps as overdensities. So we apply the clump finding algorithm at each time step. So here we are not following the same set of particles. And the trend that we observe here is even though the clump is collapsing, in the center, the clump tends to grow. So we apply the same density threshold at each time. And what we see is they are growing in mass inside, but they are also collapsing inside. So first, the first thing we wanted to test is just if we recovered the JR relation. So what I show you here is the JR relation. So again, a specific angular momentum versus radius. Every point or every symbol here is a different structure. So the color just represents the density that we use to define these clumps. The black line is the fit to the observations that I showed you before. The red line is the fit to our numerical sample. And as you can see, we recover with the same slope compared to the observation, this 1.5 slope. What is interesting here is that this simulation only contains turbulence and gravity. But again, this is at fixed time, so the first part is more related to the evolution of this angular momentum. So what I show you here is the visual evolution of a clump tracking from the past. So here the definition time is on the right. So this is the small blue or purple clump. And as we go back in time, so we see how these particles are more dispersed in the past. Here I just showing the member particles. So here in principle we have also intruder particles, which will be the blue particles. But I'm not showing here these intruder particles. About the evolution, how this evolution, like visually can be seen in the JR plot. So I'm going to start first with the plot on the left. So here again we have the JR relation. The black line again is the fit to the observations. So here I just chose 5 different clumps using 5 different density thresholds, from 10 to the 3 to 10 to the 5 particles per cubic centimeter. So here the red square corresponds to the definition time. So at these points, this is their specific angular momentum and their size. And as we go back in time, so moving to the right, we again measure the specific angular momentum as its radius. So here the color is corresponds to different clumps. What we see is that we identify 2 periods of evolution. An early one, which will be this part, with a slope very similar to that in the observations to the 1.5, and a late evolution where these clumps apparently they are conserving the angular momentum. So let's move now to the plot on the right. Here what I'm showing you is the fraction of intruder particles over time. So the particles, this yellow, this green, and the purple clumps, when in the first part of the evolution, when they present this angular momentum loss, corresponds to a large fraction of intruder particles, which will be this part. So here the definition time will be on the right, and those clumps that present 2 periods of evolution in the past have a lot of intruder particles. So again, we define these intruder particles if they are like inside the box defined by the minimum and maximum values in each axis in the coordinate. And what we're trying to say here is that if we are more particles to interact with, if we have more particles to exchange angular momentum with, then it's reasonable to think that these clumps are going to have a period of evolution, like losing their angular momentum. But once the clump is close to the definition time, where they are like more compact and we don't have a lot of intruder particles, then they are evolving, conserving their angular momentum. In the case of the clumps in the blue and cyan, these are the clumps defined with the lower density threshold, so they are like kind of large and massive. So essentially the fraction of intruder particles is low at all times. So essentially they are not exchanging too much angular momentum, and they try more or less evolving, conserving angular momentum. So this is a chaos tracking from the past. So we can also track to the future. So here, the definition time is on the left. So this is a clump, and we define a clump using a density threshold to 10 to the 4 particles per cubic centimeter here in orange, which will be this one. And then we track always the same set of particles. So as time passes, we see how some particles lower the density, so they are becoming now red particles with lower densities, but at the same time there are some central collapse. They have a few particles that are collapsing, they are increasing the densities. So essentially, we always know this happens no matter the density threshold we use to define the clumps. So we always lose some particles, even though the clump is still collapsing. So these red particles are taking away most of the angular momentum of the clump, allowing the rest of the material to collapse. So these red particles, so imagine that I define a new clump here. The new clump here will be smaller, will be denser, but if I track this clump like from the past, as in the previous case, these particles will be the intruder particles here at the first time step. So these particles are the intruders that leave the volume defined by the new clump, take away most of the angular momentum of the cloud, and allowing the rest of the material to collapse. What we are saying, this fraction of the material is taking away most of the angular momentum. We can measure the angular momentum in the diffuse and the dense part. So we just put a density threshold and say all of the particles that are above this density threshold are the dense region and below is the diffuse part. So we can measure the angular momentum over time in the dense and in the diffuse part. So these are your different plots with different thresholds, but essentially what we see is that the diffuse part is gaining angular momentum, while the dense part is losing it. Again, this can happen no matter what the density threshold we use to define the clumps. So, okay, okay, sorry for that. So our answer, or possible solution to this angular momentum problem will be something more like this. If the angular momentum is conserved during gravitational contraction, as we know, if we reduce like the size, it should rotate faster, so the rotational energy tends to increase. In principle, this should continue. This ratio, this beta parameter, which is the ratio of this rotational energy to gravitational energy, would also tend to increase. And this should continue in principle until gravitational energy equals rotational energy. And at that point, the collapse should be halted by rotation. But if we are exchanging some angular momentum via some mechanism, in our case, we think that it will be more related to hydrotorques, which is related to turbulent viscosity. I'm gonna say more about this later. Then the contraction can continue. And I'm not going into much detail here, but if we suppose that this beta parameter is constant, we can derive at some point this J relation, so having little j as the radius to the 1.5, including also some other parameters. So conclusions in the first part. We can reproduce first the J relation observed using a simulation of global hierarchical contraction, as you saw. In following or tracking these clumps from the past, always following the sensor of particles, we identify two periods of evolution. An early one with a slope very similar to that in the observations, and a late one where they are more or less conserving angular momentum. And in tracking Lagrangian sets to the future, no matter the density threshold we use to define the clumps, we always see that we always lose some of the particles, where these particles are taking away most of the angular momentum of the clump, allowing the rest of the material to collapse. This is very similar to what happened in accretion disk, where the part of the material that loses angular momentum moves inward, and the material that gains angular momentum moves outward, but here we are not saying that our clump is actually rotating. What we are measuring here is actually the residual angular momentum, so we are just taking r cross p respect to the center of mass and zooming over the particles. So at the end, we are not assuming that it's solid body rotation or something like that. Is there any questions here? I'm going to now abort the theme about the angular momentum transport mechanism.
Yeah, there are two questions in the room.
Okay.
Hi, yeah, so can you talk a little bit more about how you're going between comparisons with the observations and the simulation? Because I understand in the numerical simulations, you can measure r cross v directly. But the
Yes.
observations, you're measuring it's a line with size relationship. Is that right? And then you're doing some set of conversions to get that to be a J?
Yeah, first you need to, the first thing they do, I think, is identify a velocity gradient. Then you can plot like these position velocity diagrams and try to fit there, depend on the pattern, try to fit there like a solid body rotation. And when you have like a solid body rotation and you have the fitting in the position velocity diagram, that you can have, I think, the angular velocity. And using the angular velocity, you can compute the specific angular momentum. So you need to make some assumptions about how the object is rotating. And usually essentially the things that they plot in the J relation tend to be like a little bit like roundish. So that's the difference. In here, of course, we are not so far computing the angular momentum in that way. At some points, we need to compare with the observations. To do that, it would be interesting to have like synthetic observation and identify velocity gradients. But here so far is directly r cross p over the particles.
Yeah, I mean, so I guess, is it surprising that they agree so well, given that the measurements are quite different?
I know. I think I have a question like a few months ago when somebody asked me, okay, so you are saying that they are rotated, that the approximation of solid body rotation is like not too bad. And I say, yes, if the geometry of your clump is kind of roundish, because the center of mass is close to the density peak they use to compute or to define like the axis, no? For example. So in that case, we will go deeper in this later, but in that case, we have in this simulation our clumps said to be roundish. But something different happens if we consider elongated structure. So it depends. But yeah, so far here with roundish clumps, the agreement is like remarkable.
Yeah, that's really great how well it reproduces the slope. I was just wondering if you have a prediction, would there'd be diffuse gas escaping, like that you could see with radio or UV or something?
Sorry, can you repeat the question?
Well, I think you said that the angular momentum is being carried away by this diffuse component, and I was wondering if that could be observed, or is it too low?
Why? Yeah. What they observe in smaller regions are profiles. So what you can measure like the angular momentum for the entire object, but also you can measure it for the profiles. And you can have the profile of the specific angular momentum from 10 to the 3 to 10 to the 4 AUs. So in that profiles, they see most of the angular momentum like in the external region, which will be similar to the angular momentum in my diffuse part, in the sense that the diffuse part is here, like the external regions. So maybe not the angular momentum for the entire structure is not gonna like give you a lot of information, but profiles can give you more information about how is the angular momentum or how it's redistributed inside the structure. So our next step actually should be measure profiles. But yeah, it could be measured using profiles, I think.
Well, do you want to ask your question?
Yeah, so hi, Gers. I don't know, like an observation when there's outflows in these protostars. Do they carry away a lot of angular momentum from these outflow jets? But then in your simulation you don't have outflows. So I wonder if the observations you compare to, are they protostellar cores, or are they just pre-star, like starless cores?
That's a really good question. I'm not sure. For my simulation, of course, I don't have the resolution to reach these scales. I haven't checked if my if the structures here that I just selected from different papers in the literature will have stars or not. So far, at least in course, it could be. Now in the case of like complete molecular clouds, of course they should have a few of them should have stars also, possibly outflows. But here, of course, I cannot be sure about these objects. So, but yes, I suppose they can carry some of the angular momentum, but I think at smaller scales. So far at these scales, I don't think it should be very relevant, but to be honest, I'm not sure.
Thank you.
Okay.
I don't think there are other questions. Please proceed.
Okay. Okay, let's move on. Okay, so the next part is about the nature of this angular momentum transport mechanism. So now using another code is also an SPH code, but it's called Phantom. So it allows us to include also magnetic fields. And essentially, I try to combine these three ingredients that I mentioned earlier, so turbulence, gravity, and magnetic field. So using Phantom with a pretty similar initial condition than my previous simulation, I have now 3 new simulations. So the first one, just going from right to left, is a simulation that only contains decay and turbulence. In the middle is turbulence plus gravity, so now we are forming a few zinc particles, stellar particles. And the first one, heat image DG3, it contains the 3, turbulence, gravity, and magnetic field. So the point here is we can again try to define numerical sample of clumps in each simulation and see if we can reproduce the JR plot. So that's exactly what we did, but now we have like a combination of these 3 ingredients, right? So what I'm showing here now is, again, JR relations everywhere. So this is the JR relations for the 3 simulations. So we have only turbulence, gravity plus turbulence, and the bottom gravity, turbulence, and magnetic field. The first thing to know, well, in the simulation that only contains gravity, even though we have like most of the structure are around the black line, around the observational trend, of course we have a lack of dense structures because we have a lack of gravity. But it's interesting that we can at least reproduce the magnitude of the specific angular momentum just with turbulence. In the case of the simulation with gravity and turbulence, we see something strange because, again, a lot of the structures are like around the observational trend. Here again, the black line. We have like a family of clumps that are here inside this circle that apparently they are evolving like conserving angular momentum, which is something that is not observed in the observations, something that we didn't observe also in our previous simulation with the code gadget 2. So now we're using Phantom. We are seeing this family of clumps that we don't know what they're doing. And the plot at the bottom, well, the slope is a little bit steeper compared to the observation. Here, the red dashed lines are the fit to the numerical samples. But what's interesting here is that, again, they are more or less around the observational trend, but the scatter is reduced compared to the simulations before. Is when I saw my simulations, I saw a lot of elongated structure. I saw a lot of filaments actually. So when I just look at my clumps, like clump by clump, see like the evolution, what they're doing, I realized that some of them are actually elongated. So I decided to reduce essentially my sample. So here's just an example of one of the clumps. So we have these type of clumps. They are more the ones that have like a denser region, a collapsing region, and some filaments, some filamentary structure. So what I did is try to reduce my sample, just conserving those structures that have aspect ratios below 3. So the elongated structure with aspect ratio larger than 3. I'm removing them and I again plotting the JR relation. So in the first case, in the simulation just with turbulence, there are not too many elongated structures. So yeah, I remove a few of them, but essentially no. And again, the rest are, well, kind of along, kind of close to the observational trend. What is interesting in the simulation with gravity and turbulence, the HDG3, we now closely reproduce observational trends, and those structures that were like located around this region, then they're not there. So essentially, if we remove elongated structures, we recover more closely the observational trend. And in the case of the magnetic simulation, with most of the structure were filaments. So here, of course, I cannot say too much about a relation using like 3 points, but essentially in the magnetic simulations, most of the structure are filaments. So the way we interpret this is that turbulence can give us the magnitude. Just with turbulence, you can like reproduce or the magnitude of the observed values. But with gravity, you can increase the dynamic range in sizes. So you need gravity to, of course, reach denser regions. And in the case of adding magnetic, well, once we have magnetic field, then we reduce the scatter. So the action, what they're doing is that turbulence by itself we can recover the magnitude. With the gravity, we can expand the dynamical range in sizes, and with magnetic field, we can reduce the scatter. So if we combine these 3 effects, then we have what we see in the observations. But how do we know that which one is like the most important? So which one it's the most relevant mechanism here to remove this angular momentum? It's the magnetic field, it's gravity, it's turbulence. So we actually compute the torques, the terms on the right-hand side here. Once I define a clump, I can, well, just rewrite this equation in terms of mass, so I can just compute like the torques for each particle and sum over the particles of the clumps. And here where I show you here at the top is the magnitude of each torque, the hydro, pressure gradient, gravitational, and magnetic. Here is the viscosity is not here because we don't have like information about the viscosity in the code, but we can compute the four. And these are just separated by the density threshold we use to define the clumps from 10 to the 3 again to 10 to the 5 particles per cubic centimeter. And what we see is that the hydrotorque that includes turbulence viscosity, it's the larger. So we always see that the blue, it's larger in magnitude compared to the other torques. So essentially, our proposal and mechanism of this, our proposal like solution to solve this angular momentum problem, it's mainly at this scale, it could be mainly due to turbulent viscosity or this hydrotorque. It's still debating about the meaning of this hydrotorque, but it's essentially what we have. So again, the hydrotorque is larger in magnitude, and the magnetic, for example, it's decreasing at high densities. So a few points here to discuss. We are measuring the angular momentum with respect to the center of mass. As any other reference frames, the center of mass could be accelerated. So the angular momentum will not be conserved if we measure respect to some point that is accelerated. But if we measure the angular momentum respect to the center of mass, we can be sure that that measurement corresponds to the internal angular momentum. So if you measure respect to the center of mass, you are not taking into account the momentum, the angular momentum that comes from the bulk motion, so the clump movement as a whole, like angular momentum. And this again only happens if you measure respect to the center of mass. So that's what I was saying before with the question is that in observations, what they use as the reference point is maybe the density peak, but if you have a morphology that is kind of roundish, then the center of mass is gonna be like close to the density peak. And then both measurements, mine from the simulations and the one for the observation, should be similar. But when we have a more elongated structure where the density peak is not close to the real center of mass, then we're generating more angular momentum that is like kind of fake, that is kind of true angular momentum is being generated because of the point you chose to define or to compute the angular momentum. So again, this is the center of mass has very interesting properties. And about the meaning of the hydrotorque, because when I show you this equation is written in Eulerian. So here we define a volume, a fixed volume, even though we're using SPH, which is like a Lagrangian code in nature. So here is in these terms, this term of the hydrotorque appears like explicitly only when you write the equation in the Eulerian form. If you write it in Lagrangian, then you cannot see that this term. So in the Eulerian frame, when we define a volume, we are relating these hydrotorques to the particle flux across the volume's boundary. We be related to these intruder particles leaving or entering the volume and allowing the rest of some of the material to collapse. That will be the interpretation of these hydrotorques. If we write the equation in Lagrangian frame, we think that this effect can be seen in the change of the angular momentum due to the change in the spatial redistribution of the particles. So we can change the angular momentum if we change the particles redistribution. So if we have a more roundish clump, or we have a filamentary structure, then the angular momentum will be different just because of the shape. So here in Lagrangian, where we cannot see this term explicitly, we are kind of correlating this effect of these hydrotorques to this change in the morphology. It's still on debate. These are, of course, there are a few other comments that I've been receiving about the interpretation of these hydrotorques. So if you have other ideas, of course, we are willing to discuss it. And as I said, this mechanism that resembles to this angular momentum transport in disk. So again, here we are not saying that our clumps are rotating. So we are not identifying some pattern of rotation. We are not assuming solid body rotation. So this transfer mechanism, the way we think is something more like this. So imagine you have two fluid parcels of two SPH particles. We can decompose the velocity in some radial component pointing to the center of mass, and we have a perpendicular component. So if we have R cross B, only the perpendicular component would be the one that counts to the final angular momentum about the magnitude. So after some interaction that we think is again related to turbulent viscosity, then the particle that lost angular momentum then increases its radial component and then start falling to the center of mass, while the particle that gains angular momentum then increase their perpendicular component and then take away most of the angular momentum of the two particles. So that's more or less we think that this could be happening essentially. So this is what I mean about when I say the residual angular momentum. So angular momentum redistributed, just computing R cross B. So conclusions to this second part. So the JR relation is more similar in the simulation that contains turbulence and gravity. So again, with just turbulence, we can reproduce like the magnitude. We cannot reproduce, we cannot extend this relation to different sizes as we have if we include gravity. The simulation, when we add magnetic field, even though they are kind of around the observational trend, most of the structures are filament. And if we remove these elongated structures, well, we end up with a relation only with 3 points. And the hydrotorques, which again includes turbulent viscosity, are the dominant ones. So in magnitude, again, we think that the angular momentum at these scales, it's been redistributed due to turbulent viscosity, which is not a new solution. So Larson, I think in the 70s, proposed that turbulent viscosity like as a possible solution to the angular momentum problem. But then he discarded it because he said that there were not enough turbulence in clouds to support this possible mechanism. But so at the end, we are kind of like bringing back this possible solution. So what I'm doing now, since I have a lot of filaments, and I've been discussing this with a few of the visitors, we had it during the semester, there are only a few examples of the angular momentum in the filaments where they clearly see a velocity gradient along the minor axis. So you can think that these filaments are rotated like a cylinder, rotating cylinders, and they again need to see a clear velocity gradient, and assuming solid body rotation, that we can compute the angular momentum for the entire filament. But the question here is if they these filaments are really rotating with respect to the main axis. So this is the questions here about the angular momentum in filaments, now that I have a lot of filaments. So I can take, for example, one of the filaments in my simulations, kind of try to isolate it and just decompose in regions and try to project things and try to measure the angular momentum in these filaments. So here I show you on the right, like a section in this, I think it's the white section, and you are seeing this filament like in an edge-on view. So you're seeing the filament in this direction, and try to decompose the velocity into radial and the perpendicular component, and I see like, okay, here apparently this filament is rotating exactly just like a rotating cylinder. So that's the thing. But this filament does not contain any sinks or any star particles. When I try to look some other filaments in my simulations, where I can see like they have sinks or these star particles, I can clearly see that some longitudinal flows, I see like some of the filaments have some flow coming or pointing to a hub, and here I have some sim particles. So I'm starting to look at the angular momentum of the sink, because I can track and I can have the information of the angular momentum of these star particles. And the point here is to see how this orientation between the filament and the angular momentum of the sinks, it's evolving. As far as I know, because I'm new to this filament angular momentum orientation, this is motivated because now Shu is working with outflows also. So we're interested in comparing this outflow alignment respect to the filament. And as far as I know, we have some theoretical models that can offer a prediction of this outflow filament orientation. We have a model that predicts that it should be perpendicular, that it should be parallel, depending on how the structure is like being assembled, if they are assembled by shocks, if they are being assembled by gravity or by longitudinal flows. It should be parallel or it should be perpendicular in some cases. And the thing here is that, well, the hypothesis here would be that the first things in my simulation, in principle, since the overdensity is like formed by turbulence, then the outflow orientation, or here the angular momentum of the sink, should be in principle random or maybe parallel respect to the filament. But after some time that now gravity like becomes important, then we now have longitudinal flows. So if you have longitudinal flows and you have an offset, then you can impart some rotation. And so if we study or we measure, we quantify the angles between this angular momentum and the filament over time in the simulation, we would expect to see that maybe the first one are more random or more parallel, but after some time we should see that it's becoming more perpendicular because now we have more longitudinal flows. So that would be essentially the idea. What we are doing now, again motivated by some observational results. In general, as far as I know, this outflow orientation tend to be like more random if you collect like a different filaments using different catalogs. It should be like, it could be more random, but there are few filaments where you can observe most more of them that are perpendicular and most of them like being parallel. So it's interesting to see what is happening in those specific regions. So to do that, I just taken my simulations and try to define first the filaments. So to identify filaments, I've just been playing with these dispersed code. It's a code to identify filamentary structures. So far in 3D, measure the angles between the angular momentum of the thing, which we are assuming that is related, it's pointing to the direction of the outflow, so there's an assumption there. And see the evolution of this orientation over time, just to see if after some time it's moving from perpendicular or random, from parallel or perpendicular, from random or parallel to perpendicular orientation. So of course, now that I have new simulations with magnetic field, we can also test the orientation of these outflows or angular momentum respect to the filament and respect to the magnetic fields. So I leave you here, make my conclusions for both parts, and I can take questions. Thank you.
Have any questions? For people online, you can either raise your hand or just type your questions in the chat and I can speak up.
Yeah,
Oh.
I'm just.
So sorry, can you say a little bit more about how you define clumps in, I guess mostly in the second part of the in the second part where you include the magnetic fields and how you compare that with observations? Because again, it's a pretty fraught topic, how you decide to draw a boundary, and it looks like it's having a pretty big impact on how you draw conclusions about the momentum.
Yes, okay. Yep, let me go back to... Okay, so you say defining in general clumps, or you say in defining like filaments?
Well, I guess I'm thinking more about the second part, but you have this conclusion that your results are dependent on whether or not you include high or low aspect ratio clumps. But then I'm also wondering about how the clump definition between your simulations compares with what people are doing observationally, because it could be quite different.
Yeah, okay. Well, in the simulations, we use like a density criterion, a density threshold. So the algorithm works essentially like this. So you have particles, you like check all the particles that are above the density threshold that you set, and then you identify like the densest particle. And then around that densest particle, you have something that we call the smoothing length. So you are like all of the particles that are important to compute quantities, compute things in a test particle, all of the particles around it correspond to a smoothing length. So essentially you are just adding particles around inside this smoothing length until you have like all of the particles above the density threshold you set. So you kind of find at the end you are going to have like particles around the densest region inside the density threshold, the smoothing length, and you then move to the second densest particle and adds particle in its smoothing length. So then you end up with a surrounded a clump surrounded by particles that have the density threshold you set. In the case of filament, I can do that using an algorithm, or essentially you can do that using like directly the density threshold. So say I'm gonna take this region, this box, so show me the particles that are above some density threshold.
Sorry, so in the second simulation where you have filamentary structures, you're still using a spherical kernel when you're calculating sort of the nearest neighbors and the density threshold, so that, but even with that, you do get filamentary structures?
Yes, even though I have elementary structures, yes.
Okay.
Yeah. So essentially there are something like this. Let me see you. I show you here a few filaments, examples. It goes here. So it's something looks like this. So this is like by color by density. So essentially you have the densest particle like in the external region and a dense region inside. So in this case, if you use a density threshold, you can have still filaments. This could happen in these kind of particular filaments, but in those filaments that I showed you before, when we have like more longitudinal flows, it's a little bit more difficult to isolate the clump in that case because they are not like this. They're not like having like a density profile increased with radius, right? So it's a little bit tricky in that case, but using this algorithm, I can still have filaments.
I guess how should I interpret viscous torques in these simulations or in SPH as a general? I noticed you didn't plot them with the other torques. Are you able to estimate them from these simulations, or do you know the magnitude of the viscous torque?
Sorry, can you repeat how to interpret the viscous torque in the simulation?
Yeah, I noticed they weren't plotted in the torque plots, and I wonder if you can interpret them in SPH simulations at all.
Yeah, it's a good question about the viscous torque. The way we interpret this turbulent viscosity of the code is not like related to the code itself. I think, well, some people that I've been working with about using Phantom about the viscous, that you maybe have like a viscous profile, something like this. This is not related about that. I'm not sure if we can compute the viscous, really like the viscous, because maybe it's going to depend on the resolution, I don't know. But here, what I mean by the turbulent viscosity is it's totally different. It could work like a microscopic turbulence in the sense that you have like shear, you're kind of transporting the viscosity of some of the component to the perpendicular component. So in that sense, it's similar to the microscopic viscous. But yeah, not sure if we can measure it in SPH, but for sure turbulent viscosity is not like related to that. Does answer your question?
I guess in that case, should I interpret the hydrodynamic torque as including some large-scale viscous component, or I know there's microscopic viscosity as a separate.
Yeah, okay, I got it. So we are not adding some term in the simulations. So that to say, okay, we add this turbulent viscosity term in the equation and that to solve in the code. We are just interpreting this as the angular momentum that is being transferred due to maybe an inertia, due to an inertial phenomenon. So you are moving some particles, so this is angular momentum being redistributed due to the change in the morphology just by inertia, for example. So yeah, in the sense, we are not like adding a new term explicitly in the equations. It's more related to the way we interpret this in the code, but
okay.
Yeah.
Well, I don't know. Do we have any last questions? If no, we thank our speaker again. Thank you. We will see each other again next semester on the next already. Bye.
Thank you so much.
Yeah.
Sorry for not being there, and sorry for